So hello, today we are going to discuss about the concept of graded doping. Graded doping means the doping which are not uniform. So suppose we here we take N-type semiconductor material. This is a N-type semiconductor material whose length is L. As you can see, as this is the N-type semiconductor material, its majority carrier concentration is electron. Okay, and this electron concentration is varies with distance, as you can see from this equation. At x equal to 0, its electron concentration is maximum, which is nd0. As the length increases, its electron concentration decreases. So this type of doping is called graded doping. We can also call this as non-uniform doping. So here electron is the majority carrier concentration, uh, which is given as nd0 e to the power minus x, where a is a positive constant. Now from this we can calculate px. So px from mass action law, ni square by nx. So this is ni square by nd naught into e to the power minus ax equal to ni square by nd naught e to the power x for 0 x l. Now let's find the derivative of these two terms. First, dnx of dx which is nd naught e to the power minus ax into minus a, and dpx by dx equal to ni square by nd naught e to the power x into a. Now if we look in the semiconductor material, these are electron. As you can see here, the concentration of electron is high. Here the concentration of electron is low, so there is a concentration gradient. So electron will try to diffuse from left to right side. As the electron diffuse, it left positive ions. So here positive ions will be more. From here also electron will diffuse and left positive ions. So as the electron in left to right direction, there will be diffusion current in the opposite direction. So I can write I diff in this direction. Okay, and as the electron move from this position, left the positive ions, this create an electric field. This is known as built-in electric field, because here the positive potential is more, here the positive potential is less, so plus minus. So electric field will be in this direction. Now due to this electric field, there will be a drift current in this direction. Okay, so diffusion current in negative x direction and drift current in positive x direction. So at equilibrium, what will happen? both will cancel each other. Total current I net becomes 0. So we can say that current density J net will also be equal to 0. Okay, I hope this is clear, because diffusion current in this direction, diffusion current is happening because of the concentration gradient, and as the electron moves from left to the right location, they left positive ions that creates an electric field, and we know that the drift current will flow in the direction of the electric field, that is here in positive x direction. So drift current flow in positive x direction, diffusion current flow in negative x direction, and at equilibrium they will cancel each other, so become 0. So total current I net is equal to 0, that's for J net is equal to 0. So now we can perform some basic calculation, find out what is the electric field that is developed here. Now you can see an interesting fact here. We did not apply any external electric field, so that's why there is no current is flowing in the equilibrium. So to get current flowing in equilibrium, we need to apply external electric field. I will come to that part later. Now here what we find, J net is equal to 0. So total current density equal to 0. So current density, it is due to electron and due to hole, Jn drift plus Jp drift plus Jn diffusion plus Jp diffusion. So these are all the current component. Now as we only talk about the majority carrier concentration, so we will eliminate the minority carrier part to 0. Okay, so Jn drift can we write the next part of the equation, Jn drift plus Jn diffusion is equal to 0. We know the drift current density is sigma E, right? So here sigma E means E built in. Because of the built-in potential, built-in electric field, the drift current is flowing. So that's why I write in this way. And the diffusion current it is because of concentration gradient, which is equal to Q dN, as it is due to electrons, so dN by dx, or in our case we can write it as dnx dx. So earlier I find dnx by dx, we just need to put here. So sigma, we can write sigma, we know here will be nq mu n. So here it will be q nx q mu n to E built in q dn, and dn by dx equal to, here from here this is minus a and this term is nothing but nx, so minus a into nx. Now if we arrange the term properly, we can write the equation as equal to q dn a nx. This term can be cancelled, So from this we can find E built in is equal to A dn by mu n. We know that d by mu is equal to kt by q is equal to vt. Okay, this is an important formula in EDC. So A Vt. So here we can find the built-in potential, that is AVT. Now if we try to draw the band diagram of this, let's draw it. So here the external electric field Ext is equal to 0, and the internal electric field, which is the built-in electric field, which is AVT. We know that dEC by dx dEV by dx is equal to dEFI by dx is equal to Q into E net. E net means total net electric field. E net can be written as E internal plus E external. So in our case there is no external electric field, this term is 0, only the internal electric field, which is Q dn mu n into A, or you can write this as Q Vt into A. So from this equation we can say that there will be bending in conduction band, valence band and intrinsic Fermi level, but as the external electric field is 0, there will be no bending in the extrinsic Fermi level. It will remain 0, so no current will flow. So let's draw the band diagram here. Okay, so this is my extrinsic Fermi level, which does not have any bending. With respect to this, we have to find all the Fermi levels. Now let's draw the intrinsic Fermi level here. This is my intrinsic Fermi level. This is the conduction band. This is EFI, and similarly this is my valence band. So as we can see, as the distance is small, this gap is small, this gap is more, and as the distance increases, this gap reduces. We know an equation for a n-type semiconductor. N is equal to Ni e to the power Ef minus Ei by Kt. This is our Ef. So here we can see the initial position. Ef is greater than Ei, so N is greater than Ni. So here it is more N type, and as we move towards x equal to L, if here L is high, it try to become an extrinsic semiconductor. So this is all the discussion about the graded doping which I shown for a n-type semiconductor. Similarly, you can try do for p-type semiconductor and check the what will be the built-in electric file. Now, if I make a summary that what we have learned, so we learn that in case of graded doping, the doping is not constant; it changes with distance. So it is not necessary that doping will be of exponential form. It can be of another nonlinear equation. We have to do calculation depending upon that. So here, as we can see, as here the electron concentration is high, here the electron concentration is low, electron try to diffuse from left to right direction. So for this, what happens, or I to say positive x direction, so for what happens as electron diffusing in the positive x direction, and diffusion current is flowing in the negative x direction. As the electron move from here, it leaves out positive ions which creates an electric field which we call as a built-in electric field. The built-in electric field causes the current to flow in the positive x direction. At the equilibrium, what happens? This drift and diffusion current cancel each other and the total current density becomes zero. Then we have calculated the built-in potential from the relation, and we find that there will be bending in valence band, conduction band and the intrinsic Fermi level, but there will be no bending in the extrinsic Fermi level because there is no external voltage source is applied or energy source is applied, and later we find out what will be the graph in case of graded doping. I hope you understood this topic. So thank you.